Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to materials science and engineering, and we will extend our discussion on thermal properties of materials. So far we have discussed various concepts related to heat, temperature, the various associated properties such as specific heat, heat capacity, the concept of change of state, latent heat, uh, and other related things. So in this video we are going to discuss about another important concept which is associated again with the measurement of heat and temperature, that is heat exchange basically between two bodies, two substances, how heat is exchanged, how much heat is exchanged, how much increase or decrease in temperature happens. So it is basically about that. So it is called as calorimetry. Okay, so we'll discuss about calorimetry. So before that, just a quick recap of the basic foundation things so that we are on the same page and we are mentally tuned with what we are going to discuss. Okay, so that you don't miss out, so that you don't feel a bit deviated. So basically, heat is the total energy content of a substance, internal energy content of the substance, which is because of the internal molecular movement, and it can be of three types: translational, rotational, vibrational. This leads to kinetic energy, and this internal energy is called as heat. Now, what we understand is that heat is basically the energy in transit, that is the energy in flow, uh, energy which is moving from one body to another. As I said, heat content in isolation is never defined. You cannot say the heat content of a particular object is this much. No. How much heat is flowing from one object to another, that is defined. That you can, uh, that you can say. Okay. In isolation, you cannot say that. It is not meaningful to say that this is the amount of heat content of a body. So what defines heat movement? That is temperature. Okay. So here, temperature, if you understand, if you remember, let me again just lay it down for you. So let us say we have two objects. This is one object, and let's say this is another object. Let's say this is object A, this is object B. A has a temperature of TA and B has a temperature of TB. Now let's say TA is greater than TB. Now let's say we connect these two objects. Let's say we bring them in thermal contact with each other. So obviously here the heat will flow from A to B. Okay, from A to B. Okay, so as a result, as heat flows out of A, the temperature of TA will drop, and as heat flows into B, the temperature of B will rise. So where it will stop? At a middle temperature. So here the interesting thing about equilibrium temperature is that we know that the temperature of TA, it will decrease and temperature TB will increase. So this equilibrium temperature, that is, which will happen, both the bodies will arrive at the same temperature, which is called as equilibrium temperature, which is called as thermal equilibrium. This equilibrium temperature, it will be lesser than TA, that is the higher initial high temperature. Okay, the initial high temperature, it will be lesser than that, but it will be more than T subscript B, which is the initial low temperature, the low temperature body. So equilibrium temperature will be lesser than the higher temperature, initial higher temperature, but this equilibrium temperature, it will be more than the initial lower temperature. So both the bodies, it will arrive at the same equilibrium temperature. Let me make it clear. TA is, let's say, TH, that is higher temperature, and TB is T low, which is the initial lower temperature. Heat flows from higher temperature to lower temperature. Then when heat flows away, temperature drops down. When heat flows into, temperature increases. Both arrive at the same temperature, which is called as the thermal equilibrium temperature, and then there is no more heat exchange from one body to another. This is the simple concept. Now, this is basically the kinetic interpretation of temperature, which is the temperature of a body is a measure of the average kinetic energy of the molecules, which is defined by the molecular movement through rotational, vibrational and translation. And heat is basically energy in transit from one point to another because of temperature exchange. That is temperature difference. Okay, not temperature exchange, temperature difference. Heat exchange happens through temperature difference, higher temperature point to lower temperature point. So I also used different analogies in the previous video where I discussed heat and temperature. So now we know the difference between heat and temperature also. Okay, so basically it is a cause and effect kind of relationship. Okay, so this is the thing. Now, specific heat. Specific heat basically conveys the same information about heat and temperature through a mathematical expression. So the specific heat of a substance, it is the amount of heat required to raise the temperature of a unit mass of substance through 1 degree. Okay, so let's say we have 1 kg of a substance. How much heat should be supplied to it so that its temperature rises by 1 degree or 1 Kelvin? Okay, this. And if it is in grams, then it is in 1 degree Celsius. This is conveyed by specific heat. So basically specific heat also says that if there is a heat supply, that it is heat supplied, it is positive, then there will be an increase in temperature. Okay, heat supplied, temperature increased, heat taken out, temperature decreases. This is the unit. And basically here, this is the delta T. It is the difference between the final temperature and the initial temperature of the body. Okay, which is specified here. So this is specific heat. Now, what is calorimetry? Now the calorimetry, which is basically a branch of physics, which is the application which is used in engineering, which deals with the measurement of heat, heat exchange and temperature. So the basic principle of calorimetry is that when two bodies, there are different temperatures and they are placed in thermal contact with each other, heat flows from the body at a higher temperature to the body which is at a lower temperature till the both acquire the same temperature, and this is called as thermal equilibrium, which I just said. Now, the principle of calorimetry states that the heat gained by the cold body or the lower temperature body, the lower temperature body is called as the cold body for easier understanding. The heat gained by the cold body is equal to the heat lost by the hot body. Okay, so that there is, and here is an important assumption, that there is no energy loss, there is no heat loss in the surroundings. That's why everything, this kind of experiment is done in a thermally insulated chamber, so that there is no chance or very minimum chance of energy loss or heat loss to the outside. So the heat gained by the cold object or the lower temperature object is equal to the heat lost by the hot object. Okay, so let's say this is the hot object and this is the cold object. So the amount of heat which is lost or goes out from the hot object and the amount of heat that goes into the cold object, they must be equal in magnitude. Direction will be opposite, that's why the negative and positive sign will come, but now just understand that the magnitude, they will be the same. Okay, so for this purpose a special instrument is used which is called as a calorimeter. So basically it is a copper vessel, a cylindrical copper vessel basically, and other designs can also be there, but simplest construction is a cylindrical copper vessel which has a wooden jacket around it for thermal insulation, and it is provided with a stirrer. And the wooden jacket, the space between the calorimeter and the jacket, it is again provided with some extra heat insulating material like glass wool or anything, so that another extra layer of protection for thermal insulation is provided. Okay, so this is way this is the way through which the calorimeter gets thermally isolated from the surroundings. So this is the basic design. So we have a copper vessel, we have a wooden jacket, we have thermal insulation like glass wool around it, we have a stirrer, and a temperature measurement device such as thermometer is used to record the temperature. Okay, now to further minimize the loss of heat due to radiation, the outer surface of the calorimeter is polished than the inner surface. Okay, and some extra holes are provided so that we can insert the stirrer and the thermometer into it through these holes. Okay, now the operating principle. Let's say we heat a particular sample, a substance, whatever substance it is. We heat that sample, let's call that sample or substance X. It has a mass m subscript x and a specific heat Cx to some known temperature, to some known higher temperature. So this is the internal system, internally how it looks like, where the sample X is placed inside the calorimeter. It comes in contact where the sample, it has a temperature, a higher temperature Tx, and it has a mass mx, the hot sample or the hot object, and the water, it has a temperature Tw and mass mw. Okay, and there is a stirrer which is placed to continuously stir so that for even heat distribution it happens, and the temperature is measured with the help of a thermometer. So this is what the inside of a calorimeter looks like. Okay, where the hot object, the sample which is to be tested, is placed inside the calorimeter containing water, and there is heat exchange between them, and then we measure the heat exchange through the use of specific heat equations. So here we have taken a sample or a substance X, its mass mx is known, and it is heated to a certain higher temperature which is known. Okay, mx Tx, mass of the substance, temperature of the substance. Then this mass is placed in a vessel containing water inside the calorimeter. The calorimeter has water inside. The water, the mass of the water mw and the specific heat Cw and the temperature Tw is known. So the water is at a lower temperature than this heated mass, okay, which is specified by this Tx greater than Tw. So obviously when the two substances, the higher temperature mass Okay, let me use a different ink here. So obviously when the higher temperature mass is brought in contact with the lower temperature water, there will be heat exchange, and this heat exchange will be from the higher temperature to the lower temperature. So as a result, the temperature of Tx, it will get lowered, it will decrease, and the temperature of Tw, that is water, it will increase. The water will get heated. Now when it will stop? Till the temperature Tx gets lowered and the temperature of Tw increases to the same level, and this same level is called as the thermal equilibrium temperature. Okay, the thermal equilibrium temperature, where the thermal equilibrium temperature will be lesser than the higher temperature and the thermal equilibrium temperature will be greater than the lower temperature. So it is lesser than this initial temperature of this mass, this sample, and greater than the initial temperature of water. This is the critical thing, and this is the final equilibrium temperature, TE. Final equilibrium temperature, TE. Now our objective is to find this equilibrium temperature. How can we find this equilibrium temperature? So this can be done through this. So there are many things, many equations, but here the specific heat equations will be used. So when the sample X is placed inside the calorimeter in water, heat is lost by this sample, heat goes out of this sample to the water. So the sample X, it loses heat. So here to signify heat loss, we'll use a negative sign. So we know the basic formula of specific heat and heat, that temperature which relates both, that is delta Q is equal to mc delta T, where delta T is final minus initial. Now the initial temperature of the heated mass, it was Tx. This is the initial temperature, and the final temperature of the sample X, it is the equilibrium temperature. Okay, so this is Tf minus Ti, and minus sign to signify heat loss. Okay, then the heat is lost by the sample. Okay, the heat is lost by the sample, but the water, it gains heat. Okay, the water gets heated. So here the heat gain by the water, it is also expressed in a similar way using this formula, delta Q is equal to mc delta T. Here we take the mass of water, the specific heat of water, and this again the final and initial temperature. This is the initial temperature of water, Tw, lower temperature, and this is the final temperature, Tf. Because both water and the unknown substance, they arrive at the same equilibrium temperature, the same final temperature, because of the thermal equilibrium concept. So here for the mass, we have the mass of the substance mx, the specific heat of the sample, the substance x, Cx, and final minus initial, Te minus Tx. And here it is the heat gained by the water, that is mass of water, specific heat of water, final temperature minus initial temperature of water. Here plus sign indicates heat gain. Okay, now Tx is greater than Te, Te is greater than Tw. Now as per the concept of calorimetry, heat loss is equal to heat gain. This is the most important principle of calorimetry. And here the important consideration is that provided that there is no heat loss to the surroundings, because otherwise this equation fails. So you cannot completely ensure 100% the 100% guarantee that there will be no heat loss, so always a margin of safety, margin of error is considered. Okay, so that is the principle, but here for discussion purposes we'll consider that there is 0% heat loss. So heat loss is equal to heat gain. Okay, so the amount of heat lost by the hot object is equal to the amount of heat gained by the cold object. So if we equate these two, that is minus mx cx t minus tx is equal to mw cw t minus tw, we will have, taking this minus sign, multiplying it with this bracket inside, so we have mx cx tx minus t. Here it was t minus tx, here it is tx minus t. Now we have the specific heat of the sample Cx is equal to mw cw t minus tw by mx tx minus t. This is the standard expression. Now you can utilize this to calculate any of the parameters. If one thing is unknown and the other things are known, you can calculate Cx, you can calculate the mass of water, you can calculate the mass of the unknown substance, you can calculate the equilibrium temperature, you can calculate the temperature of the water, the temperature of the substance, the specific heat of water, but specific heat of water is known, there is no need. So if you want, these are the standard things which are generally calculated. Whether you want to calculate the specific heat of the unknown substance or its mass, the mass of water which is used, the equilibrium temperature or the water temperature, the initial water temperature. Okay, but the initial water temperature is always recorded, so again no need for that. So if you get problems or questions, it will revolve around any one of the following parameters, and the other parameters will either be given directly or you have to calculate them through other ways. So this is the general principle, the standard equation of calorimetry, which specifies the specific heat of the unknown sample, the substance which is initially heated and placed or tested in the calorimeter, because this is the primary test material. Okay, this is the primary test material. Okay, this thing. Okay, this is the sample or test material, and it has to be tested, whether it is for its mass, whether it is for its specific heat, whether it is for its temperature, whatever it is, it has to be tested and it has to be evaluated. So this is the standard expression of calorimetry. Again, it is based on the principle of heat and temperature, heat exchange, specific heat, and some standard equations which we used and then equated them as per the calorimetry principle, provided that there is no heat loss to the surroundings. Okay, so this is the